Alrighty, Muso here. Let's talk about simple harmonic motion. What is simple harmonic motion? And to best describe simple harmonic motion, I'm going to define two things, periodic motion and then SHM itself. So periodic motion, and we're going to toss this down with a series of examples, but really vis-a-vis a definition. Periodic motion is when an object vibrating or oscillating, okay, back and forth over the same path, with each cycle taking the same amount of time. Okay. For example, we've got a mass and spring system. You can even see one over here. As it goes back and forth, as long as no energy is introduced or taken away from the system, it will go back and forth periodically or predictably. Okay, so word terms that we use to describe periodic motion would be oscillating, periodic, vibrating, vibratory. We'll even discuss simple harmonic motion under the same umbrella. Okay, so these are all just terms really for the same type of deal. When an object is within simple harmonic motion, it's periodic motion plus a little bit more. So it's oscillatory or periodic. However, there's also this extra bit that needs to be enforced. The net force acting on that object can be described via Hooke's law. Now you may recall Hooke's law from the energy unit. It's okay if you don't. I'm going to better or redefine it right now. But when we're dealing with springs in the energy unit, Hooke's law said that the force coming from that spring was equal to negative kx, with k being the spring constant or force constant, and x being the distance the object was displaced away from its equilibrium position. In addition to that, Hooke's law says that that force, which is also considered a restoring force, must be proportional or linear to our displacement. So as that x increases our displacement away from equilibrium, the force will also increase in a linear manner. There's no exponential relationship here, no trigonometric functions that we're dealing with yet. This is simply a linear relationship of the restoring force being proportional to the displacement. Now I'm going to talk about Hooke's law and simple harmonic motion more down in this diagram. Before I do that, let's just look at this simulation, which is modeling Hooke's law. You notice as that object is displaced to the right, the force is to the left, and as that object gets displaced to the left, the force ends up being the opposite. That's what the negative is for. Okay, so the negative is just for directional information. Once again, Hooke's law says that that restoring force is going to be linear to our equilibrium or to our displacement, and it'll be opposite into the direction of our displacement. Let's look down here in this diagram where we have the same spring modeled over a series of different steps. In the very beginning, we took an object that was attached to this spring and we displaced it to the right, to the positive x position. Right before we let it go, we notice that that spring is pulling it back in. It's trying to restore it. It's trying to get to go back to its equilibrium spot. So the object is displaced in the positive sense, but the force acting on it is left or negative. We also notice at that instant the object has no motion. Its velocity is 0. Okay? Then we release this object. As we release it, that spring pulls it to the left. And as it travels to the left and it gets to the original equilibrium position, the force acting on it actually disappears. The spring is where it wants to be. It is no longer pulling on the block. Not only that, the block is traveling the fastest it can possibly travel, and it's traveling at Vmax. Vmax is actually negative because the block is traveling to the left. So in the very beginning, the block was 0, V was 0. Here, the velocity is to the left. Now, because it's traveling to the left, even though there's no force acting on it, an object in motion will remain in motion. So it's going to continue to travel to the left. And as it does that, it's going to start to compress that spring. The object will eventually get as far to the left of the equilibrium position as it started to the right of the equilibrium position. So it'll get to a negative x, or negative my maximum displacement. When it's at that negative x position, it stops momentarily. The velocity is 0. It's to the left, but the force acting on it, the spring, will now push to the right, or it'll be positive. That object will then start to head to the right, eventually passing the equilibrium position again. This time it's once again going to be at maximum velocity, but now it's at maximum positive velocity because it's headed to the right. So in this scenario, v is to the right. Our spring is in its equilibrium position, so the force acting on it is 0. But of course, an object in motion will remain in motion, and it'll eventually get back to its positive displacement, just as it was in position A. And it'll repeat this process over and over again. The fact that it repeats the process over and over again allows us to define this as periodic. And because that force acting on it will always be opposite to the direction of my displacement, and it'll always be linear to my displacement, it is going to abide by Hooke's law, hence it is considered simple harmonic motion. Now for a series of the next remaining videos, I'm going to describe simple harmonic motion with the spring system. But I need you to understand that simple harmonic motion can be defined or can describe many different objects, types of motion, not just a block on a spring. You're gonna see us discuss this with a pendulum going back and forth. You're going to see me talk about it in terms of uniform circular motion. Another good example that's given is if I were to take a bowl, nice round bottom, and I were to take a marble and place that in that bowl, that marble is going to want to roll, and it's going to roll past this natural spot and then stop, and it's going to come back. And it's going to rock back and forth, back and forth. And as long as there's no energy loss, it'll remain in periodic simple harmonic motion. Okay? I think that's it. That's a good introduction to SHM. The next videos, I'm going to break it down in more detail. Hope this helps. Thank you.